Hello. In this video, we're going to be looking at how we can use the sun and time to be able to determine your longitude. We're going to be starting off by thinking about the time zones and the position of the sun. Now, any time in the day, one point of the Earth is directly facing the sun. It is at this point that the sun is at the highest point in the sky. It's local noon. And as the Earth rotates, the point that is facing the sun slowly changes, moving around the globe. Let's look at the Earth from the position of the sun. So the part of the Earth that you see here is currently facing the sun, and it is midday at location 1. Now as the Earth rotates, let's see 20 minutes of rotation, and this isn't to scale. You can see that location number 1 is no longer directly under the sun, but location 2 is. Location 2 is now at midday, whilst location 1 has moved into the afternoon and it's now 12:20 here. This continues, and now location 3 is experiencing midday, and it's 12:20 at location 2 and 12:40 at location 3. Now, if you wanted to use the sun to set the time, this would be a good way to do it. But there's a problem. Locations that aren't too far away from each other have different times. And this could cause confusion if you're going to meet, say, at 12:30 in the middle of these locations. So to make it easier, we group these areas into zones with a common time, say 12 o'clock, where all locations share the same close time. We call these imaginatively time zones. And then the next location has another time zone, generally grouped in hour blocks, getting later as you go round the globe and earlier on the other side. Now this seems very simple, but it doesn't take into account borders of countries which do not follow simple mathematical divisions of the globe. So in reality, it's a little more complex when we're dealing with real life. But we'll keep our simplified model for the moment. So you can use this fact to determine where you are on Earth. Say, for example, you're on a boat in the sea here, and you know that it's currently 10 o'clock. You phone someone back at your home, and they tell you that the current time there is 12 o'clock. Well, you can use this fact to determine how far away from them you are. We know that the full degrees around the globe was 360. And we know that the Earth rotates through this amount in 24 hours. So if they are 2 hours different in time, then the Earth has rotated 1/12 of the way through a full spin. Dividing one side by 12 and then the other, a 12th of 360 degrees is 30. So you know that you are 30 degrees away from them in longitude. Fantastic. Now again, we need to think of the practicality of this. It wouldn't work if everyone was comparing to their home, as this would mean each measurement was just based on where you lived and wouldn't be useful across the globe. So we needed to settle on a base point from which to measure longitude. Greenwich was eventually chosen as the base point from which longitude is derived. The prime meridian representing 0 degrees, with anything on one side of it being east and on the other side west. Now let's take our points from earlier but look at them in a bit more detail. If we wanted to work out how far point 1 was from point 3, then we could use more precise measurements of time based on measurements from the sun. Here we can see that there are 40 minutes between them. We can use this to work out how many degrees of longitude separate them. Now we know that to travel 360 degrees takes 24 hours. And so to convert 24 hours into minutes, we just multiply it by 60, which gives us the time for a full rotation as 1,440 minutes. Now we know that there are 40 minutes separating them, and to get to 40 we have to divide by 36. And if we do the same to the other side, we can see that they are 10 degrees. So we therefore know that there are 10 degrees difference in longitude between point 1 and point 3. Okay, so we've got that worked out, and then using measurements of the sun we can then determine the difference in longitude. Surely there are no other issues. Well, there is one. The sun doesn't actually appear to move through the sky at the same rate. Sometimes it can be a bit fast, and sometimes it can be a bit slow. And this is where the equation of time comes in. We can use it to correct for the fact that the sun may not be at its peak directly at noon. So if you were in a location, you could use a shadow stick to determine when local noon is. You can then correct it with the equation of time if the sun is a bit fast or slow, and this is how you do it. So as the sun moves through the sky, the shadow cast by a stick will get shorter. Now at this point, when the shadow is shortest, the time in Greenwich Mean Time, was 6 minutes past 12. You'd get this by looking at your watch. But the apparent solar time is 12 o'clock, as this is the time when the shadow was shortest. You can see as the day goes on, the shadow starts getting longer again. However, on this day, the equation of time was plus 4 minutes. This means the sun was a bit fast, and so what we thought was 12 was actually 11:56, as the apparent solar time 12 minus the equation time 4 gives us the mean solar time of 11:56. We can then work out the difference between Greenwich Mean Time and mean solar time, which is 10 minutes, the difference between 12:06 and 11:56. And then we can work out how far away we are in terms of longitude. Now we know from earlier that to go 360 degrees round took 1,440 minutes, but we've only got a difference of 10 minutes. So to get from 1,440 to 10, we divide by 144. And what we do to one side, we do to the other. So therefore we know there is a difference of around 2.5 degrees. Now we need to determine, are we 2.5 degrees west or east of Greenwich? Well, if it's east, the mean solar time would be later than Greenwich Mean Time, and vice versa for west. As the mean solar time is 10 minutes earlier, we know we must be west of Greenwich, so the location's longitude is 2.5 degrees west. Right, that was a lot of information, so let's have a look at some questions. Here we have Albert, who set up a simple shadow stick that created the shortest shadow at 11:56 GMT. On the day that Albert carried out his experiment, the equation of time was plus 5 minutes. Determine Albert's longitude. Well, firstly, we'll work out the mean solar time by subtracting the equation of time from the apparent solar time. So the mean solar time equals the apparent solar time, which will be 12 o'clock because that was the time that we had the shortest shadow, minus the equation of time, which on that day was plus 5. So the mean solar time is 12 minus 5 minutes is 11:55. Then we need to work out the difference between Greenwich Mean Time and mean solar time, which is nice and simple as there's only a minute between them. Greenwich Mean Time being 11:56, which it tells us in the question, and mean solar time being 11:55. So therefore the difference is 1 minute. We then need to convert a minute's difference into degrees. So again, we're going to use what we used earlier, that 360 degrees takes 1,440 minutes, but we don't have 1,440 minutes, we just have 1 minute. And so to get to that, we need to divide by 1,440, and we do the same to the other side, which gives us 0.25 degrees. And then we need to decide if it's east or west. Well, as the mean solar time is earlier than Greenwich Mean Time, it's 11:55 compared to 11:56, we therefore know that it would be west of Greenwich. So the longitude that Albert is at is 0.25 degrees west. Finally, this question. A ship has been sailing for some time, and on one particular day the captain uses measurements of the sun's altitude in the sky to deduce that the local mean time is 12 noon. The ship carries an accurate clock that tells the captain that the time in Greenwich at that moment is 10 minutes past 2, and you need to determine the longitude of the ship. Well, firstly, we want to work out the difference in time between the ship and Greenwich. And the difference between 12 and 2:10 in the afternoon is 2 hours and 10 minutes. And then we want to convert this into degrees. So again, we're going to use the same conversions that we were using previously. So I've converted 2 hours 10 into minutes. So 60 times 2 is 120, plus the 10 minutes gives us 130 minutes. And then to get from 1,440 to 130 minutes, we divide by just over 11. And we need to do the same to the other side. And doing that gives us a difference of 32.5 degrees. Again, we need to work out if it's east or west of Greenwich. And as the time 12 o'clock is earlier than 2:10 in the afternoon in Greenwich, we know that the person is west of Greenwich. So therefore, their longitude would be 32.5 degrees west. So now that you've mastered working out the longitude, have a go at our key questions.